Hey there, AP Calc fans. I'm back with another video. It's over section 2.3. In the textbook, this section starts on page 58, and I would encourage you guys to read through all of the theorems that they give you. Pretty much the sum of everything is that they're showing you what you're allowed to plug into straight away and what you're not allowed to plug into straight away. There's tons of limits that say you can split up. Just for instance, if you can talk about the limit as x approaches any variable a, and you're saying, hey, I'm adding two functions together. They're saying you can kind of separate it by saying take the limit of f of x plus the limit of g of x. And you can do that with subtraction. It's the limit of f of x minus the limit of g of x. And you can do it with multiplication too. The limit of f of x times the limit of g of x as you're approaching a. And you can do it with division. And there's just a ton of rules that they kind of just throw at you. So what I did was I took one of the examples that they had in the textbook and I morphed it just a little bit to show how you can use all of those properties in tandem on one kind of example like this. So essentially, as long as the limit, how should we say this? As long as the number that your x is approaching in your limit does not violate the domain rules for each individual piece of the function, like x to the 2/3, you can take 8 to the 2/3 power. You can take the square root of 8. The bottom part, this is a polynomial, so you can certainly plug in 8 there, and 8 does not violate the rules of that domain. And as long as these two subtracted from one another aren't 0, you can just do a straight plug-in of that limit. And here's what it looks like when you use the properties of all those limits. You can break this apart and say that this is the limit as x approaches 8 of the top divided by the limit as x approaches 8 of just the bottom. And I'll just say minus 16 over x. Really no need for parentheses here. But then I can break it down even further. I can say this is the limit as x approaches 8 of x in 2/3 plus the limit as x approaches 8 of 3 root x. And maybe these should be put in parentheses. Those are the things you're taking the limits of. Over the limit as x approaches 8 of 1/3 x squared minus the limit as x approaches 8 of 16 over x. Yeah, so the limits are very invasive. They get into everything. They get into your numerators, into your denominators. They break up addition. They break up subtraction. There's even a rule in there that says you can plug into, where was it? Yeah, if you have fractional exponents, you can just do a straight plug-in. So I'm going to go over here. The limit as x approaches 8 of x to the 2/3 is 8 to the 2/3. All right? There's actually a rule, too, that says this 3 can come out in front of the limit so that you're just talking about 3 times that limit, which is root 8. All right? And then any polynomial, it talks about how you can just do a straight plug-in on any polynomial because they don't have any domain issues. And then there's another rule that kind of talks about if it doesn't violate the domain of a rational function, then you can just do a straight plug-in. Which, I guess, suffice it to say, we kind of talked about this last year with computational limits. And in a sense, it looks a lot like section 2.1. So, I'm sorry, you couldn't see that last part. I'll do better. Simplify as best you can without a calculator. What I mean by that is you can look at x to the 2/3 as the cube root of 8 squared, which 8 itself is a perfect cube, 2 times 2 times 2. So that's like the cube root of 8 times 8. So it's going to be 2 times 2, 4. Plus the square root of 8 is 2 times 2 times 2. You can take out a pair of 2's, 2 root 2. You can square 8, which is 64, times a third, which would be 64 thirds. And then 16 over 8 is just 2, which would be the same as 6 thirds. And that gives you 4 plus 2 root 2, all divided by 58 thirds. And here's a clever way you can reduce a fraction like that. If I multiply the top and bottom by 3, so multiply the top by 3 and the bottom by 3, it gets rid of this 3 in the denominator here, and then you're left with 12 plus 6 root 2 over 58. Divide this by 2, and this by 2, and it simplifies it to 6 plus 3 root 2 over 29. All right, so a lot of that was just a review of things that you've seen before and probably knew, but maybe just, didn't hurt to get a refresher on that stuff. Let's try some examples from page 66 on. So check out number 7. All right. You investigate. We've got a rational function. Is this a domain issue? Setting the bottom equal to 0 will give us x equals negative 3/4. This is not a domain issue. Plug in. So this is the limit of the top, which is negative 2 minus 5, over the limit of the bottom, which is 4 times negative 2 plus 3. Negative 7 over negative 8 plus 3, which is negative 5. It's 7/5. So we can just do straight plugins at times. Check out 21. So you can start by asking yourself the question, can I plug into the bottom and the top 1/2? Well, 1/2 squared is a fourth. A fourth times 6 is 1.5. Half of 7 is 3.5. 1.5 minus 3.5 is negative 2. Negative 2 plus 2 is 0. So the denominator is 0, which means we have to do some algebra manipulation to both the top and the bottom. It appears the top's factorable and the bottom's factorable. Remember your special cases, not really special cases, but just this idea of if it's a minus, then a plus, then you know these are both going to be minus, minus. Okay? 12 Factors of 12 that add up to negative 7 would be negative 4 and negative 3. So you know that you have to get, well, first of all, this is going to be, the only way to get 2 is negative 1 times negative 2. So how do we get 4, negative 4 and 3? I'm guessing this would give us negative 3, and this would give us negative 4. And if you check your work, 6x squared minus 4x minus 3x plus 2. If you're guess and check factoring, if that didn't make any sense, just go through the AC method, splitting the middle up and factor by grouping. Okay? But it is nice to have that shortcut in your back pocket if you understand what's going on. Kind of like here, the only way to get 2x squared is to take 2x times x. And I need to get a positive 6 and a negative 1 to add up to 5. So positive 6, negative 1, that's kind of an easy way to figure out that factoring. But you know what? Before we even did this factoring, I should have recognized that x equals a half was going to be that was the problem. And when you think about what x equals a half is and where it came from 2x equals 1. It came from the 0, 2x minus 1 equals 0. I should have known that that was going to be one of the factors of both the bottom and the top if we were to gain any ground on this rational function here. All right, we should be able to plug in now. A half plus 3 divided by a half times 3 minus 2. So you got 3.5 on top and 1.5 minus 2 on the bottom, which is 3.5 divided by negative half. So another way to think about that would be 7.5 over negative 0.5. Which is the same as 75 over negative 5 if you multiply the numerator and denominator by 10, which gives you negative 15. Okay. What else do you guys want to talk about? $25 looks good. $25 involves the kind of factoring that you guys don't normally do on a daily basis. Is it x squared or x to the 4th? Yeah. That's what I thought. It's a big boy. Alrighty. So we've got a domain issue instantly. If I plug negative 2 to the 4th power in there, it zeroes out the bottom. So I got to think factoring. This is a difference of two perfect squares. X squared minus 4 times x squared plus 4. Furthermore, this difference of perfect square breaks down to x minus 2x plus 2. And this is still a part of it. So we can rewrite our denominator just like this. Now the numerator has an interesting pattern of factoring. I know that x plus 2 is going to be a factor for x cubed plus 8. If I can't remember the formula, I just go to long division, which is x cubed plus 0x squared plus 0x plus 8, and just divide by that x plus 2. It comes out to be x squared 0. 0 minus 2 is negative 2x squared. Drop your 0x. Minus 2x. Okay, so it's x squared minus 2x. Minus 2x squared. Remember, we're just trying to always cancel out the leading term in this long division. 0 minus negative 4 is positive 4x plus 8. Plus 4. 4 times x is 4x. 4 times 2 is plus 8. And everybody's gone. It factored perfectly. Yeah. A cubed plus b cubed, if they're both perfect cubes. A plus b. A squared minus ab plus b squared. All right. I know that's a hard one to just remember at will, but long division's fun. Those two cancel out. And now we should be able to plug in negative 2 for our x's. So, plug it in. Negative 2 squared. Negative 2 times negative 2. Plus 4. Negative 2 minus 2. Times negative 2 squared. Plus 4. It looks like 4, 8, 12 over negative 4 times 8. Cut it in half. Cut it in half. You got negative 3/8. And there's a whole bunch of other types of examples. I really just want you guys to explore this kind of on your own beyond this. And yeah. Section 2.3 is just a lot of computation, a lot of just soaking in the reading material from that chapter, and that's all I got to say about that. All right, thanks for watching.